Life is full of decisions. Purchasing a new car or home, choosing the right job, determining the best time to invest money are all personal choices. More complex decisions are made by groups of people, companies, research institutions, government agencies, in the areas of purchasing, trade, and finance. Right now, I'm standing next to University of Maryland construction site located on the College Park campus. How was the decision made to build here? The analytic hierarchy process, developed by Thomas Sadi, accomplishes decision-making by breaking tough decisions into their component hierarchies. Because these decision hierarchies can sometimes be quite large, we believe the Treemap, a visualization tool developed here at the University of Maryland's Human-Computer Interaction Lab, is an effective tool not only for visualizing the decision process, but also manipulating it. In the University of Maryland's case, the decision was made to place this building right in the center of campus. The behind-the-scenes factors in this decision were quite complex, ranging from architectural issues to impacts on campus traffic to electrical and plumbing connections. Processes like the AHP help in these decisions, and tools like the Treemap help bring the AHP and this building to life. The decision to construct a new building depends on social factors, such as the relocation of current workers and the location of nearby schools or hospitals, economic factors, such as property investment and wages for new workers, and technical factors, such as accessibility of the new site or environmental building codes. Already we've defined the first level of our decision process hierarchy. This is the first step of AHP. As you can see, the complete tree can grow quite large. This is only our initial attempt at the problem. Note we have 3 levels of factors to consider. For example, if we follow one particular branch under economic factors, we find initial investment, which itself is composed of electric supply, site improvement, and building cost. Now admittedly, things can be broken down further, but we'll keep things simple for this example. To complete the tree, we place all of the solutions to the problem underneath all of the lowest level subfactors in the tree. If we're considering 4 sites, all 4 of those sites occur beneath each of these branches. Doing this completes the first stage of AHP. To evaluate the tree, each factor in it must be considered separately. For each factor, all of its children must be prioritized in the context of that factor. This is done by comparing the children with each other 2 at a time. For example, let's consider driving road. Site A has a 2-lane road right near it, making it 3 times better for driving accessibility than Site B, which is located near clogged city streets. Site A is only half as desirable as Site C, however, as Site C has a major highway exit nearby. Similar comparisons can be made for each group of children in the tree. Numeric priorities are then developed, and an overall ranking of sites is achieved. Fortunately, computer programs exist to handle this part. However, obtaining an overall picture of your data and the factors that went into your decision is difficult. Let's see how Treemaps can help with this problem.
During the past 3 years at the Human-Computer Interaction Laboratory, we have been studying the visualization of large hierarchies of information. We've applied our Treemaps approach to the visualization of the contents of a hard disk on a computer, to basketball statistics, and to the visualization of large libraries using the Dewey Decimal System. Now we're applying the Treemaps to business decision-making processes.
This application, developed by visiting HCIL researcher Toshiyuki Asahi from NEC Corporation, visualizes the AHP process with a Treemap. The entire decision hierarchy is contained in this rectangular screen area. The first level of the hierarchy is created by vertically slicing this rectangular region. Social, economic, and technical factors all are first-level factors. Their proportions reflect the priorities established with the numeric weighting previously mentioned. Economic factors dominate, with about a 42% priority. 9 additional subcriteria are displayed when the next level is revealed. An important point of AHP is thus visualized. Large priorities on parent factors, such as economic factors here, greatly impact the priorities of their subfactors. Areas for labor, transportation, and initial investment are thus all increased by the dominance of their parent economic factors. Note that this level was created by horizontally slicing the first level factors. The alternating slicing with each level is a property of tree maps and is used to display as much as possible on the screen. The next level switches back to vertical slicing. Finally, the 4 alternatives, coded by color and sliced horizontally, are revealed. This application performs the actual calculations necessary for the decision. The bar chart below the tree map displays the quantitative results on which site should be selected. In this scenario, Site A is a clear winner with an overall priority of about 0.30. Site B has a 0.26 priority and is followed by Sites D and C. These priorities will always total to 1. The tree map can display at a glance the factors that heavily influence the decision. Site A's product transportation capabilities played an important role in its eventual selection. Relative to the other sites, its priority was 0.63 for this criterion. Its absolute importance among all criteria was 0.05, or 5%. Other important factors were the skills of the labor force and the wage rates that would be paid at Site A. Site B can be seen to have strong results in business transportation, but not enough to tip the decision in its favor. Suppose we wish to see how a more favorable wage rate would affect Site B's overall priority. A hook tool can be used to manipulate the priorities of siblings in the tree. Selecting the border between Sites A and B under wage rate, the priorities between the two can be adjusted, while not affecting their siblings' priorities. As this occurs, the overall priorities of the two sites change. Site B is seen passing Site A's priority as the other two sites remain constant. Giving labor the hook, and then economics, reinforces B's strengths and thus increases its overall priority. Restoring the original view, we can utilize another tool at our disposal, the pump tool. This tool allows the priority of any criterion to be altered, but unlike the hook, it changes the absolute priorities of all the other siblings, not just the sibling next to it. For example, pumping up working environment, and then social factors, will benefit the site that dominates these particular criteria, in this case Site D, eventually affecting the overall decision. For a closer look at different areas of the tree map, the zoom tool is used. This tool is useful for allocating more space for detailed portions of the hierarchy, as well as making finer adjustments with the hook and pump tools. Note that pumping up Site C's priority on driving road to 1 after zooming in on the environment still is not enough to make it our overall choice. The diagram can be easily zoomed back out to once again view the complete picture.